to Ecotech's electrical engineering capstone presentation. For our project, we really wanted to put together a conglomerate of everything that we've learned here at Ecotech. So our project covers sustainability, renewable energy, AC and DC fundamentals, motors and controllers, and it covers process control. So I'm the project manager, and the most difficult part of being the project manager with this specific team was idea control. Because there were so many ideas when it came to this that we had to pick and choose, and we decided to come up with the best idea to really encompass everything that we've learned with our electrical engineering degree at Ecotech. So my name is Matt Milstein. I was the project manager on this group, and I was responsible for keeping everybody on track. I was responsible for deadlines, making sure that everything got done on time and that we were ready and left plenty of time at the end for experimentation. May I introduce Eddie Ramirez. This was our design engineer for the project. Eddie was responsible for everything as far as how it looked from the beginning, where things were going to be put, what colors were going to be used, and everything that had to do with the design of this project. This is John Siedler. He is our electrical engineering engineer, electronics engineer, excuse me, and he was responsible for deciding what circuits we wanted to put in there, where they needed to be, how they needed to be wired up. When it came to, after the initial prototype, how it needed to be cleaned up and everything. I'm sure he'll get more into that later. This is Mark Randall. Mark Randall was our research engineer. Mark was responsible for going through and deciding what we needed to focus on with this project to keep within the scope, because obviously you could go a lot of different directions with this project, but for our presentation today, we're focused mostly on the electronic side of things. So, our objective for this project is we wanted to liberate the people from big oil, and we wanted to give people the choice of natural living. And above all, since structures such as this already exist, we wanted to take it to the next level. We wanted to fully automate it. We didn't want to go from one part where you need to pay for your electricity, you're on the grid. We wanted to take you off of that. But once you're off the grid, we don't want you to be a slave for your own home. We want you to be able to go on vacation, leave for a few days without your home not going down on you. So we've taken care of that, and we've automated all the process that go into a natural living home. And now I will pass this off to Eddie Ramirez.
Morning, everybody. So one of the biggest challenges we had was to save power, save energy. So we were wondering, how are we going to do that? What would be the best way to go about it? Well, as you can see here, 43% of all the energy that's used inside your house is for space heating and cooling. So that was the biggest chunk we want to get rid of. The next biggest was 12%, which was water cooling and heating. So with that in mind, we said, what can we do to automate this system to make it something natural where we don't have to spend our money, where we don't have to, give an arm and a leg for this. So this is what we tackled. We started doing thermal energy storage, which is the battery you will see in a minute. Active passive heating and cooling, and I'll show you how that works. That's where you're going to save your big bucks. Sun heating water, why not use the sun? It has the most power, it has the most energy. We have photovoltaic charging system to keep everything running. We have and also water collection and storage. In a normal Earth ship, you would have to take showers, wash your dishes, or use any kind of water to make sure your plants get water, to make sure the system keeps going. So in a sense, it kind of makes you a slave to your own home where you can't go on vacation. You can't leave the place for more than 3 to 4 days. Well, that's not very fun. So our main power is going to be from the sun. And why not? So we have a controller regulator to control, as you can see right here, which has everything we need: overload protection, short circuit protection, undervoltage protection, and protection from lightning. This is very critical because if this is our main power source, we don't want it going down at any time. Next slide, please. And now I'll show you the biggest part of our project and how we tackled the situation. So this is a natural convection system. As the sun heats up the greenhouse, hot air will rise. And through this vent that we created right over here, when the temperature gets to a certain point, this will open up along with these, allowing the hot air to escape and the cool air to come through. It doesn't show you right here, but we have these geothermal cooling vents. They're buried underground around 6 feet where the temperature is about 55 to 60 degrees. Very cool. So as soon as these vents open up, it's going to let the hot air rise, pull in 55-degree air, cooling down the living space. Now the living space is going to be a different temperature from the greenhouse, because the greenhouse you never want it to get lower than about 80 degrees. So we actually control that through this as well. As soon as it gets too hot, lets all the hot air go in, cool air cools down, and then we'll shut down as soon as it cools down again. And after that, I'm gonna pass it on to John Seidler.
How you guys doing today? So yeah, I'm going to talk to you a little bit about our precipitation collection and distribution center. This is our main breakdown of how our water is going to be gathered, processed, and used through our system. We have our 3 settings here. We have our rainwater collection, our cistern water tower process, and our irrigation system, which I'll go into a little more detail now. So first we have our cistern. Our cistern is our first step. As the rainwater comes down, it's going to go into the cistern. As the cistern fills, we have a few things going on. We have a water filtration system where we're only allowing so much water to be pumped out of the cistern. Any given day, we want there to be X amount of water in the cistern so that particulate can settle to the bottom, so we're not pumping gritty water through our irrigation system. We also have our water level detection. Inside of our cistern, we have an ultrasonic sensor that is detecting how much water is in the cistern to then communicate with our water tower. Like here we have our sensor-controlled water pump. That's what I'm getting at with that, is that that's communicating with the water tower to tell the water tower when the cistern is above a certain level of water, it needs to pump into the water tower. We also have water aeration, where the pump motor is constantly pumping oxygen into the pump as it's filling the water tower. Here we have our water tower. The water tower is the next step in the process. It's where our main reservoir of water is going to be. It's going to fill based on the cistern level being too high. And in the top of our water tower, we have obviously the sun hitting it. For our example, we use clear. You'd probably ideally use black to heat the water up a little bit more. And then we also have a hydrostatic water system in there with the pressure being built from the gravity in the top of the water tower, which plugs into our solenoid valve. Here in our irrigation system, we'll talk a little bit more about the gravity-fed system coming into the ball valve. We have our ball valve being controlled by a soil hygrometer. The hygrometer is in our gardens, reading the moisture in the system to communicate with that, whether it needs to open or close to pump water in from the water tower. As the plants get drier, you'll notice the pump will fill, the ball valve will activate and allow water to seep through. Here we have grow your own food, smart farming. Obviously, the Earthship process is all about being able to create your own food, be able to sustain yourself in your home, and this allows you to do that. And I'll pass it on now to our research engineer, Mark Van.
So as you can imagine, with a project of this scale, we have so many processes going on. We ran into some problems. Fortunately, we were able to conquer most of those. Some of them not quite in the ways we were imagining originally. We were originally going to use stepper motors for our venting system, and after trying to complete the code and everything for that, we ended up scrapping that idea and going with servos. Servos were a breeze for us to use, and when you see in our demonstration, it's very easy and the code was much more simple to write. A lot of the project was actually more on the mechanical engineering side, and some of our issues came up there, which we ended up just making it happen, and everything worked out well as far as the structure and the gaskets and everything like that. We were able to get all the fittings, and we ordered a bunch of them, and we got the ones that fit. So for our project goals, when we sat down and we talked about this project, I think the key word that we came up with was automation. We wanted to make the shred completely automated so that, as Matt said earlier, you could leave your house for days at a time. You wouldn't have to worry about your plants dying on you. You wouldn't have to worry about pipes freezing or anything like that happening. So this is just a scale model And obviously, we would have many more systems in a life-size project. But we've got most of the systems in place, and we really achieved everything that we wanted to do for this project.
So I'll talk a little bit here. This is our Gantt chart. This is just kind of a breakdown of the processes that we had to go through to get the project to where it was. Just real basic, kind of talking about the weeks that we started. As you can see, we started with the structure and establishing what we were going to do really early on, week one. We were able to establish what we wanted to get together pretty early on, and then went straight into formulating code with the sensors. Spent the majority of the time getting the code right with the sensors, make sure we could format everything to fit the way we wanted it to. And then we had the research, obviously, which to make sure we had the knowledge that we needed. And that was throughout the entire process as well. We did get a chance to do the mock presentation, so that's why we had 75% there. But other than that, everything else was able to come together, and we got our final product the way we wanted it to be.
This is my part. So what we really wanted to do was have two drivers. Honestly, the rain and the sun, because we wanted to blend technology with nature. So when it rains, it goes straight to the water cistern. Then we have the water level sensor. Depending on how high it is, how low it is, pump on or pump off, send it to our water tower, which is gravity fed straight to our normally closed ball valve, which would only open once the soil hygrometer says it is too dry. So as you can see, this flow chart is pretty complicated, but we have, as the sun comes up, it'll grow the medium, heat up the plants, cause evaporation, dries up the plants, therefore it's setting that in motion. Solar panels charge our batteries, basically that's how we use that for. So our main drivers, we really wanted to use this to hit on the head. You know, we're trying to combine technology with our natural forces. Next slide.
Okay, this is our wiring diagram. We used Fritzing software to make this diagram. It was pretty easy to use. The only part about the Fritzing program that I didn't like is they don't update their sensors and their pictures enough. So that's why we had to fill these all in with these little tags to tell what everything is, except for, as you can see, the picture of the LCD and the Arduinos. And with this wiring diagram, you can wire up this entire system yourself after you build it, and you will have no problems. You can wire this up. You have to have the coded later. You're going to go to the next slide there, Mark. This is our wiring schematic. This will give you a little bit better idea and a little bit cleaner setup to how you would have to wire up the system. This is done using Tina software. It's a little more difficult to use and not as user-friendly as the Fritzing, but as you can tell, it comes out a lot cleaner, and you can really tell what's connected to what. And as far as where the nodes are, the nodes will tell you that there's 3 connections and you've got a connection. Anywhere that there's not a node, the wires will, of course, cross over the next wire. Go ahead, Mark. Okay, so this is our first code that we had for our ventilation system. This is the code for the servos. You can see that it fits on one page. Here labels what it is. This labels what pins on the Arduino that the different sensors are connected to. And then as you're coming along, you have your void setup. This is where you actually name your servos. In this case, this is named my servo and my servo 2. You come over here to your void loop, and you put, when the temperature is above 70, your first servo is going to go to position 0. And so that's going to open. When the temperature comes up, your vents are going to open. This is for the first servo. Servo 2 is here. Same deal. When the temperature goes over 70, this servo is going to tell it to close. And when it goes below 70, it's going to tell it to open. And when it goes below 70, they're going to close. Next slide. This is the code for the moisture level sensor. This is another short code. It was relatively simple. All the Arduino code is open source, so once you download the software, you can go into the actual Arduino software and you can pull up a lot of these codes for these sensors and then modify them accordingly. But you can see this one's connected to pin A1, that's an analog pin, and then the ball valve itself, it's a solenoid ball valve, that's connected to a digital pin 8, cisterns connected to digital pin 9, and the ultrasonic sensor for the trigger and the echo, it's an input and output, is connected to D11 and pin D12, which is digital. And so now we have our other sign pins, which this is where we name the pins to what we want them to be. And then up here at void setup, this is where we declare whether it's an output or an input. Of course, the echo pin is going to be your input, and that's going to be where it listens. And then this is set up in the loop where if the sensor is above 900, which means it's dry, it's going to click on the ball valve, which as a normally closed ball valve, it's going to give it voltage and open the solenoid and allow water to flow in. Go ahead and look. This is our LCD system to display. This was the biggest code that we had to deal with. They won't even all fit on the same slide. The entire code is in the binder for you to see a little further. This one only came all the way to the first one right here with the living room temperature. The greenhouse sensor and the humidity just wouldn't fit on here. I just wanted to show you which pins they were connected to, and then in the void setup, this is a lot of code that was just open source code that makes it work. But yeah, you can see the code in the binder for yourself, full code. Go ahead. Okay, so take this one.
So here we've got our detailed budget. Matt did most of the ordering online for most of our parts, and we also used a number of the items from the school. But even with using the stuff from the school, we priced it out so that you could recreate this project using our budget with completely new material. This is just more of the materials list. We've got a couple pages of that. What's more detailed about every single component that we've got in our shred project. And at the end, as you can see, one material we do have that is priceless, the top of the treadmill, which we use for the roof of the shred. That was generously donated by Matt. So our total came out to $376. We were budgeting a little bit higher, actually, about $600, and we ended up coming under budget. So this is a project that if we recreated it, we would probably fine-tune a few things. We wouldn't order quite as much as what we did last time. However, we still came in under budget, and I believe that this is, for what we created, it's a very efficient project.
You guys like to come up?